So it is very nice to have Andrés here. Andrés is one of the key figures in the literature of explicitly explainable artificial intelligence. I think your paper is the most philosophically quoted one in the literature. But so it is great to have you here. You have, how do you want to distribute the time?
Half an hour?
You have an hour, so half an hour, 40 minutes?
40 minutes.
So
yes.
When you have spoken for half an hour, then I let you know.
Yes. Okay, great. Well, thank you, Maria, and thank you, Miguel. He's not here, but for organizing this event. I've learned a lot about understanding. This is the target of my talk, the black box of artificial intelligence. But unlike previous talks on artificial intelligence in this conference, I won't be talking about LLMs. I won't be talking about whether AI understands anything. I will be talking about human understanding of artificial intelligence. Also, I won't be talking about generative AI. I will focus only on the type of AI that performs tasks of prediction and classification. For example, in medical AI, whether an image can be classified as a cancer patient or ID a certain face. That's the kind of tasks that I will be concerned with. And it's called the black box of AI simply because these are very complex algorithms that process billions of data points. They have hundreds of hidden layers, and they're non-symbolic. So basically, no human being can really understand what's going on inside the box, how the AI performs the tasks it does. However, there is a need to somehow penetrate the black box, to somehow understand a little bit, at least, of what's going on for many reasons. One of them is for legal reasons, because, for example, the GDPR requires companies who use algorithms to explain the logic behind some of the algorithms they use for automatic decision making, for example. Also, in terms of trust, so there's mixed evidence that maybe explaining how AI works makes people trust the decisions more, although the evidence is mixed, as I said. And also because even computer scientists themselves need to know more than simply the input-output relationship, because they need to debug the models, they need to improve on the models. So there are several reasons why we need to do all those things, and that's what XAI is supposed to do. XAI is a field of AI that tries to make the black box less opaque. But the main problem is that conceptually, there is a mess in terms of the way that people use these concepts. People talk about explainability, interpretability, understandability, transparency, and there is no one unified meaning for any of these terms. So one has to read part of the paper to understand exactly what they mean by any of those terms. So a couple of years back, that was not expected. Okay. Okay. A few years back, Erasmus and his colleagues published a paper in Philosophy and Technology, and the paper basically claims that we can they can help with this conceptual mess by giving us a precise sense of explanation within AI. And what they want to do is to adapt the concept of explanation from philosophy of science to AI, and they want to do it directly. They don't want to adapt it, to change it. They just say that it is perfectly possible to adapt for well-known accounts of explanation of philosophy of science and adapt them to AI. So their challenge is to show that that can be done. And the four accounts are very well-known accounts: Hampel's deductive and inductive statistical models, Salmon's causal mechanical model, and the mechanism view, which has been developed by several philosophers. And in a later paper, they even include Kitcher's unificationist theory. In the interest of time, I will only talk about the first two, which are very well known, And I will show several things about their attempt to adapt explanation to the context of AI. But the most interesting thing about their paper, to me at least, is this thesis, which they call the indefeasibility thesis about explanation. So what they say is that the features that make something an explanation turn out to be invariant with respect to the complexity of both the explanans and the explanandum, and that adding complexity to the explanation of the phenomenon does not entail that the phenomenon is any less explainable. So in the case of deep neural networks, the idea is that if you can explain a very simple network using any of these theories, then you can explain any neural networks of any complexity. So therefore, they think that they can apply these accounts to any network with any level of complexity. It doesn't matter how much data or how many layers it has, you can do it. And my main claim in the paper here is that that thesis is either trivial or it's false. And that what the thesis is saying is completely runs counter to what many people in the XAI community understand by their mission to clarify or to explain AI. So why is it trivial? Well, at some point, what they say is that an explanation can be understood simply as the causes, the entities, the states that produce an output within a model, within a system. Not a description of those states, not a mathematical expression of those states, but the states themselves. And they attribute that view to Salmon, which I think is mistaken. And in my view, that's just a trivial way of understanding what an explanation is. It's just saying, well, everything happens for a reason. There's obviously some process. There's obviously some mechanism within the machine that produces the output, but that doesn't help us at all to understand or to do anything about what's going on within the machine. So it's basically the idea that what happens within a network is not magic. So that would be a trivial way of understanding this thesis. But let's be more charitable and say that maybe what they mean is that an explanation is just a true text, an explanatory text which we take to be true because most people want to respect the effectivity condition for scientific explanation. So if you take an explanation to be an explanatory text, it is a truthful description, then that sense of explainable, the modality here is something is explainable, is logically dependent on whether you can verify that a certain explanatory text is true. If you in principle cannot verify whether any explanation is true, then you cannot argue that everything is explainable. So definitely there's a logical connection between explainable and verifiable in this case. And what I'm going to claim here is that most explanatory claims in the context of deep neural networks are unverifiable. And sometimes we can't even frame or construct or build an explanation of anything that's going on. So in that sense, the indefeasibility thesis about explanation will turn out to be false, which is what I claim. Okay, so but before we move on to the details of their approach, we have to understand a little bit about how XAI works. There are two main approaches to try to explain or to open the black box. One approach is what's called the local post hoc interpretability methods, in which the explanandum is some specific output or prediction or classification made by the machine. And these XAI methods try to pinpoint the features that were responsible for that prediction or that outcome. This is an example that's very well known. On the left, you have an image of a plastic frog, I guess, and some model predicts that there's a 54% chance that that's a frog. And what the method does is that it starts deleting parts, megapixels in the image. It does many operations of deleting the megapixels until you get a locally weighted regression that tells you exactly which are the megapixels in the image that are most responsible for the original prediction. So this only works for that image. It only works for that specific outcome and for no other. And this method has the particular problem that it's not easy to generalize. If you show it a slightly different frog, just very slightly different, the explanation might be entirely different. So it's some people say that this is a case of understanding why the image was classified in that way. In the paper that Maria mentioned, I argue that that's not the case, but we can take it up later. The other method is a global interpretation method, in which you take as your explanandum not a specific output, but the entire model. So what you do is that you build a simpler model, a toy model, sometimes they call it, which could be a decision tree, a linear approximation or something like that, in which somehow represents the larger model. So, for example, you have a deep neural network with an input and a prediction. It's a black box model. We don't understand what's going on in there. But you can distillate, that's sometimes they use that term, distillate a surrogate machine learning system, in this case, a very simple decision tree, which will give you an explainable prediction because you understand the tree. It's easier to understand the branches and how you get the output. Obviously, the surrogate model will not be as reliable as the original model, because otherwise we wouldn't use the black box model. But it will be an approximation. It will be good enough for some purposes. So and especially it might be good enough to make people understand the logic behind the model. So those are the two main approaches. This will be like a case maybe of global understanding, what's going on in the model. So if we go back to the original proposal of Erasmus and his colleagues, we have to be very careful about what those four theories of explanation, of scientific explanation, are doing. First of all of those theories are only explain individual facts or particulars, things and events. They don't explain theories or laws or systems. They're explanations of particular things. So in that sense, the only way in which they can give meaning to the word explanation within AI would be in the case of local post-hoc interpretations, because it's the only XAI method, let's say, that only focuses on specific predictions. It would be an incomplete account of explanation because it wouldn't account for the global approach to XAI. So that's the first clarification. So what exactly do they mean by the reduction or the semantic reduction of explanation in AI to any of these theories? So let's consider the case of Hempel's deductive nomological explanations. So everybody knows how it works. You have a bunch of laws, you have a bunch of initial conditions, and deductively, the combination of those two things should deductively entail the explanandum. That's how it works. Here, I'm going to focus on the laws. What exactly would be the laws involved in explaining a prediction of a deep neural network? In the case of Hempel, he framed the way that we talk about laws in terms of logic. You have a universal claim for every x. If x is p, then x is q. That will be a very simple expression of a law. And the question then is, what is P and what is Q in the context of AI? What could be the classes that we're talking about? So you could think that maybe the classes are classes of inputs, or classes of features within the inputs. And I'm going to show that that doesn't make any sense. So let's say that we are going to create a law-like statement at least, in which we correlate certain classes of inputs, for example, pictures of cats, with the prediction that the image is an image of a cat. So in that case, the law is false, because this kind of systems are not perfect. They often make very obvious mistakes. So you cannot really talk about a universal generalization. And even in the case of features within the images, if you say, for example, no, it's not just the class of cat pictures, but only certain pictures that have, for example, where you can clearly see the mouth of the cat or something like that. But even in those cases, you won't get a perfect correlation between inputs and outputs. So it doesn't make sense to talk about laws in those terms. So what exactly do they mean? I'm going to quote the paper of Erasmus, and what they mean is this. They say a deductive nomological explanation of how the deep neural network assesses an input image involves listing the weights attached to each and every node and the informational routes indicated by each and every edge at every convolutional stage, and the weights of the fully connected network along with the assigned numerical values being fed into the input layer and the network architecture. Okay, that's a mouthful, but basically it says you just have to describe the network. And describing the network means the weight given to every single connection between every single node, the biases of every single node, and then the way it was trained. In other words, a full description of the network will give you a deductive nomological explanation according to them. And initially, one might think that there is a certain similarity between what they're saying and scientific laws. In other words, if you think of laws in science as mathematical functions, and if you think of the nonlinear function, which is being performed by the algorithm, well, there's a certain similarity. But the problem is that to say what the law is in human understandable terms, in other words, to be able to operate with that explanation, to use it in any significant way, one would have to find a way to translate the mathematical information which is given by the weight in the nodes and the architecture of the algorithm, which is accessible. I mean, it's not opaque in the sense that you cannot know exactly how the network operates in terms of weights and biases. You can use a program to reach the mathematical information within the network, but that information doesn't mean anything to a human. Doesn't correlate with anything in the input image or in the output prediction. It's just a bunch of numbers, and there is no way in which a human can make any sense of those numbers and turn them into concepts, into some worldview that will understand exactly what's going on. And also, even if we could do that, we would have to verify those laws before we can build a true explanatory text and apply it to that machine in particular. And none of those two things can be done. So if you can't really express the laws in human understandable terms, you don't really have an explanation at all of what's going on. You just have a mathematical description of what's going on in a network, but that's not helping anyone understand exactly what happened and why the model ended up giving us a certain prediction. So none of those conditions can be fulfilled in deep neural networks. Therefore, I think that Hempel's deductive nomological explanations are inapplicable in any possible way to machine learning. So what about Hempel's inductive statistical explanations? Maybe those work better in this case because, well, the correlation between the images and the predictions is not perfect, but it's probabilistic. So the way that Hempel's model works is that you have, again, some laws. In this case, they are probabilistic laws. It says that the probability of P given Q is equal to R, and some initial conditions. those two things combined should give a high probability to the explanandum. And initially, Hempel said it has to be very high. He never says how high, he just says much higher than 0.5. But his initial framing of IS explanations was that the explanandum was to be expected. In other words, if you have that law and those initial conditions, the explanation makes the explanandum highly likely. So again, the question is, what exactly are those P and Q involved in the probabilistic laws? That's the same question than before. Now, in this case, Erasmus cannot go and say that the P's and Q's represent the parameters in the network. In other words, the weights between the nodes. Because once a model has been trained, there is no probability involved. The model just operates in a fixed way, and there's no probabilistic variation between different predictions that the model is making. So it doesn't make any sense to talk about the parameters in this case. So the only options we have left is, again, to go back and try to see if we can frame a law in terms of the relation between inputs and outputs, and maybe in that case we can somehow build an inductive statistical law. Okay, so the idea would be to say that the law would be something like the probability to have a cat prediction, given that you have a cat image, is equal to R. And that R has to be very close to 1, so the model has to be very reliable. But if that's your law, then it's hard to see how it's playing any explanatory role, because the only reason why we would use that model, the only reason why that model would be acceptable, is precisely because it's a highly reliable model. So we already know that. We already know that the model is highly reliable because it has been tested, and there's a high correlation between showing it some pictures of cats and the fact that it predicts that it's looking at a cat. So it doesn't provide any independent reasons why the model is highly reliable. The law itself is an expression of the reliability of the model. And the same goes if we go to the features in the input space. For example, if you say the probability that the prediction is correct given a set of features is equal to R, and we have exactly the same situation. We have a high correlation between certain features in the images and the predictions, but again, that's just another way of saying that the model is reliable. And what we want to know is, why is the model reliable? And that's not given by simply framing a law in those terms. And in general, I think that the whole project is entirely misguided. And the reason why it's misguided is that in both cases, we're talking about covering law models of explanation. And Hempel was very clear that his account of explanation was not meant to be used just to explain certain specific things. It was trying to explain general kinds of phenomena. So there's a quote from Aspects of Scientific Explanation, which says, a statement which is logically equivalent to a finite conjunction of singular sentences, like the description of the network by Erasmus, for example, and which in this sense makes a claim concerning only a finite class of cases, does not qualify as a law and lacks the explanatory force of a nomological statement. Law-like sentences, whether true or false, are not just conveniently telescoped summaries of finite sets of data concerning particular instances. So if you take this seriously, and I do, then the idea that you can take a specific model and turn a mathematical description of that model into a law, of course, runs entirely against this idea of this general project of what a scientific explanation is. And for the reasons that I gave before, I think that doesn't make much sense at all. Now, the other three cases that I mentioned in the beginning, Salmon's causal view and the new mechanistic view and Kitcher's unificationist view, have basically the same problems. So it doesn't make sense to go through all of them, because in all of those cases, the problem is that whatever you do with, whichever way you analyze a specific model, it will always come out as an explanation which doesn't really look very much like the types of explanations that we are used to in the philosophy of science. Okay, so it seems that if you look at the literature in computer science, it seems that computer scientists are not very, they don't have much faith that there will be a unified account of explanation of what an explanation is. And these are two quotes from two very famous computer scientists. And what they do is they try to change the question. And they say, the question of interpretability in machine learning, they define it as the ability to explain or to present in understandable terms to a human. And Miller says that interpretability is the degree to which an observer can understand the cause of a decision. Of course, they're not philosophers, so they're not giving us an account of understanding. So they just kick the can down the road and hope that somehow philosophers will come up with a theory of understanding that might fit the bill of telling us what it means to understand a system. So in previous work, I have defended the idea that there should be what I call a pragmatic turn from trying to develop accounts of explanation for the case of machine learning, and that we should focus instead on trying to say whether a specific AI model explains or not. And I guess what's missing is a more robust account of understanding for machine learning systems. One advantage of this idea is that, well, we don't have to define what an explanation is, and it also allows many paths towards understanding. So you can use local methods, you can use global methods, you can use example-based methods, which I didn't even mention. There's a huge family of different approaches to try to make sense of what an AI model is doing. So if we focus instead of understanding instead of trying to say what all of those methods have in common, we have a much easier, philosophically clear way of saying what those XAI methods have in common. And this idea that you can use all sorts of methods is also connected to a certain advantage that I see in talking only about understanding, and is the fact that we cannot obtain factivity for explanation in the case of AI. It's just impossible to obtain factivity. We cannot even frame the laws. We cannot even ever know which function is being performed by the algorithm. So if we have to give up the idea of activity, I guess if we talk about understanding, it might be much easier to find an acceptable way to see what all those methods have in common without having to appeal to truth. So what's missing here is some way of, what time do you have? Okay. So what's missing from this paper from 2019 is like a more developed account of understanding in machine learning, what I have in mind. And here I can just give a very brief outline of what I have been thinking about this specific problem. And the first thing is, when you think of a machine learning system, it's obviously a complex system, with many moving parts, with many different elements, many different variables. And well, as many speakers before me have remarked, there's obviously some sense in which we need to make sense of the connections between all of those different parts. So this is a quotation which is expresses that idea: understanding requires the grasping of explanatory and other coherence-making relationships in a large and comprehensive body of information. One can know many unrelated pieces of information, but understanding is achieved only when informational items are pieced together by the subject in question. So we can think of many examples. For example, Tokyo subway system, which is incredibly complex, or the stock market, or the market crash, one of the many market crashes. Any of those things are extremely complex events, and understanding them requires understanding the relation between many different parts. So the question is, how should we understand that grasping connection in the case of machine learning? And here I adopt the idea that understanding in machine learning should be seen as a success concept. And what I mean by that is that when a user or a developer uses an XAI method, doesn't matter which one, the outcome should be that the person should be successful in using that system. It should be an actionable system. There should be a way in which the person can modify some of the parameters and make it and see the changes involved in that operation. But the person should be successful. For example, if you ask for a bank loan and the bank loan is rejected by the algorithm, then understanding the algorithm, understanding the model implies that the person should understand how he or she should be able to change their situation so that they will be able to improve their chances of getting a loan, for example. Maybe they need to increase their income by $5,000 or whatever, but it's the successful use of the algorithm which helps us say that the person understands the algorithm, understands the AI. This is not a definition of understanding in AI. This is just a criterion that I'm trying to frame in this case. And this is not a new idea. This is something that has been defended, for example, by Khodorkovsky and Velikovsky, which are two great philosophers and not very well known, in their inferential conception of understanding. So what they say is that understanding is about the capability to put one's knowledge to use, to understand is to be able to tell what would have happened if things had been different, what would happen if certain things were changed, and what ways there are to bring about a desired change in the outcome. So also, for example, Hank Direct also argues that genuine understanding manifests itself as a skill. An agent must have the ability to use his or her knowledge. And since Direct is basically interested in scientific explanation, scientific understanding, what he means is that a person should be able to construct a successful model with the right idealizing assumptions. If one is able to build a successful model of a given phenomenon, then that means that you understand, you're able to use your understanding, you're able to use that grasp of the connectedness of different data points to build a successful model. But that's not the only use. Sometimes people always think of very, very sophisticated contexts, but if I understand the stock market, for example, I can also try to game it. Well, it's very hard to game the stock market, but I can profit from it, definitely. Or I can try to fix or improve a system. And all of those things are ways of being successful, successful in the manipulation and the use of my understanding with a given system. So I think that that type of use of a model is a clear sign that the method that has been used, the XAI method that has been used to make the system more transparent, is a good one, because the person is being able to use the system successfully. And we don't need to really define exactly how why the method is being successful in helping the human. We just know that the human successfully uses the given method. Now, many of these philosophers, I have another slide. Yeah. Many of these philosophers use counterfactual reasoning as a very important element within the idea of using a system. So many of them think that if you are using a system correctly, then you should be able to frame correct counterfactual inferences from it, to draw correct counterfactual inferences from the system. But the problem that I see with this is that if you think of counterfactuals just in terms of whether I change this pixel within the image and then it's going to give me a different prediction, or if I change this specific data point and it's going to change the classification, I don't think of that as genuine counterfactual reasoning. I have a much stronger view of what counterfactual reasoning is. I think that counterfactual reasoning requires theory. It requires a model of what's going on. And that model of what's going on, that theory, those background conditions are the ones that enable a user to understand how the system would change. You need to know all the space of possibilities, and that's only given to you by a theory. So if we just, to go back to Tanya's talk maybe, it would be a combination of an account of understanding which is based on the success that the users have using it, but also you need to have some kind of model in your mind so that you can correctly frame the counterfactual inferences that you're supposed to perform. So it would be a hybrid model in that specific sense. That means that if you think of global XAI methods, those methods that try to explain the entire system, those are the ones that are going to give you the complete view of the model. And I think those are necessary components of every successful understanding of a machine learning model, and especially of an opaque deep neural network. Thank you.
Explain. Before going to the questions, people in YouTube and Zoom, you can ask in Spanish still. The students here are going to ask in Spanish if they want, if not in English. And so now, Otavio, Dave, Stephen, and Francisco, and then.
Thanks, Andrés. This is a great talk. I think you're exactly right. And I want to just suggest, can you make even a stronger case about the inapplicability of the deductive homological account? Because laws are more than just true generalizations, but even on handles of it, they have to have some necessity, right? Also, they have to support some counterfactuals. And it's not even clear how any of those things would pan out in a network. Like, what are the laws there? Right? In this robust sense that is required. So it seems that it's not even the ballpark to begin. Now, one worry I had, even though you're right when you complain, say, look, in the way that some of the computer scientists formulate their account of laws in that context, you point out, well, those are mathematical representations that need not be human comprehensible, which is true, although that's not a requirement for Handel. Nothing in his account it requires us to understand the laws. Right? He assumes that we understand them, but in principle, we could have extremely complicated laws that no humans could understand. Right? I think that the point you're making is right. So given the specific dialectics of the debate, right? Because that's one of the things they want with explainable AI. But I don't think that actually counts against the DN model.
Okay. Well, in terms of the necessity component, I guess Erasmus could just reply that you get the necessity out of the mathematics, of the mathematical relations between the different parts of the network. So that wouldn't be a concern in that sense because, I mean, it's right there.
Mathematical statements are not necessary.
Depends on
your vast conditioning. You assume certain things that are also depend on other things. But okay.
Yeah, okay. I would have to go back to Hempel's text to be more clear about what you're saying, because of course the universe has laws, and we should be able to derive everything from those laws with the appropriate initial conditions, and we probably have no idea what those laws are at this point. But at least they should be understandable. They should be. We should be able to know what those laws say, and if you can't translate in any imaginable way the mathematical components in the network to concepts that exist in any mental model, then I don't see how they should be called laws to begin with.
But that's an epistemic constraint.
Yeah.
Laws are physical things, right? They need not just your own frames, right? Look, probably you're right in the sense that Hempel would not want laws that are too complex, right? But I think that's a dramatic fact about our methods for certain things, right? Now remember, for him, we get understanding out of explanation, not the other way around. But he thinks, well, once you have an explanation, you can ask, well, why we understand, right? Because we explain, right? So, he has a narrow understanding of what counts as understanding.
And he is always trying to diminish the importance of understanding of to top that up. So I guess if you operate within the framework of Hempel, I think you're right. But if we think of how we view the role of explanations within science now, then there would be additional reasons why we wouldn't want to have laws that we can't even comprehend. Yeah. Thank you.
Talk about applying the Apple models to neural networks. You looked at global laws that take the inputs and the inputs and outputs, but it seems to me that if I tried to explain how a neural network works, I would try to break it up into steps. And just picking up a concrete example, you might say something like, things like, okay, so this layer, so these first two layers detect edges and encode the position of edges in such and such way, specifying it mathematically how they're encoded. And then after that, these other layers take the edge information and combine it in such and such way to detect shapes. And then you go like this. You'd expect that this would work like this. And at each of these steps, you could have something like statistical laws that describe what's happening. So if you have two edges, then you have a shape. It could be like one statistical law that you could formulate, something like that, right? So that seems to be how an explanation should work. And I can see that sort of illuminating how the network works and giving you understanding as well. But so that's not, so that seems to be like the better way maybe of trying to apply this model.
Yeah, you can do that. I mean, you can take the convolutional steps and try to analyze whether you're looking at an edge or looking at something else. But the way those things combine afterwards within the neural network is a black box. I mean, after the initial steps, you get extra steps which are completely opaque to you. And
you can detect, some higher level features, like are there many shapes in the same vicinity, and then you can kind of we can figure out more features like that. But ultimately, leading to is there a cat or not? There's going to be a cat if there are enough of the relevant, shapes, cat shapes. You could kind of do it all the way.
Right, but I mean, the idea is that you have, let's say, a million pictures of cats, and you have to find a way to correlate some feature within those images with your output. And even if you have those intermediate steps for one image, you can't generalize it to every single image or every single feature in every single picture. So again, the question would be, whether that piecemeal description of what happened in this specific case, even if you get some more information, can be then turned into an explanation based on laws. And I think that's a step where that's a step you can't take.
I don't see why there couldn't be generalizations that work for all the inputs. Like the edge detection, that could be true of all the inputs, and it could be true for all inputs that if they are 3 edges in the same vicinity, then these nodes here will be activated in such a way that indicates that there is a shape, for example.
Right.
Like that, these could be completely general principles.
But then the network would never make mistakes. I mean, why? If
So these will be exceptions. They'll be true generalizations. Statistically, like most of the time when there are 3 edges, this will.
But once the model has been trained, those things are going to be fixed, right?
Yeah.
And you'll still get lots of errors after the training. So if we get a positive explanation of why it works in some cases, you would need to find a negative explanation as well as to why it makes mistakes in other cases. So there would be the beginning of an explanation, but I guess we would need more to get the full explanation, and that's where I don't see how we would be able to get to the heart of the problem.
An input where that's an exception to the statistical law at some level, right? So there'll be cases like that, and there could also be cases where the model is just mistrained, like at each step it worked as your laws are describing, but actually the result is the wrong output. That's just because these laws don't cover all the cases correctly.
Right. I guess you're thinking about the way that these networks detect, for example, numbers. That's the typical example that you learn when you're learning machine learning, computer vision. How it finds the edges in numbers, and it can detect which number it's looking at. That's a very simple classical example. But if you're looking at an X-ray, which has a lot of information, and it's not just a question of finding the edges or finding the shapes, but rather finding some element which is not humanly detectable in the X-ray or in the picture of a mole, then the example becomes much more difficult to frame in those terms, I think.
There is a Stephen, but there is a comment, I don't know, in one live chat about Otavio's comment that maybe laws are metaphysical, but explanation is epistemic. So that's a section.
That's correct.
Stephen.
Thank you, Andres. I really enjoyed that. So you quoted and praised that passage by Kurakowski and
Milikowski, yeah.
So I'm wondering if I'm just trying to understand your view better, and I wonder if this is a congenial way of thinking about your view, or whether you'd be sympathetic. So they emphasize the idea of difference makers. Mm-hmm. And one thing you might think is that when you're trying to understand, say, explain why someone's loan was approved or rejected, what you're often interested in is identifying whether factors like someone's race made a difference or someone's sex or whatever it be. So here would be the theory when you're trying. So explanation is often not like what are all the factors that led into this, but just did these factors make a difference, or did these factors did the pixels on some image of a suspicious mole made a difference. So then the theory of understanding would be something like you have understanding comes from knowledge of difference makers, or being able to identify the difference makers. Understanding comes in degrees, so you have more understanding, the more difference makers you can identify, but often you just want a very targeted question, like did race make a difference? So is that congenial to your view, or would that be like a different view than you're adopting? Yeah.
It would be congenial, but the main difference with the theory, the inferential theory of understanding that they propose, is that they are still thinking that understanding should be factive. So the counterfactuals have to be true in all instances.
Whether race made a difference or whether the size of the mole made a difference.
I mean, the problem with counterfactual thinking in machine learning is that there is no principled way of changing the variables. I mean, you can adjust different variables to different values and get the loan. And some of them will raise the probability that you get the loan more than others, but it's more the combination of those. The variables are not independent in many cases. So I'm highly suspicious that you could get just like the one change that would change the decision. I think there are many different ways of doing it, and all you need is a way for the user, in this case the client, or the bank client, to understand that it's the combination of these two or three variables in different set in different ways that would make a big difference. So it doesn't mean that that's the optimal way of doing it, but it's a way of changing the outcome. Thank you.
There's Francisco, then Dana, then Jake.
Thank you for the talk. I was wondering two things. One is, as previously discussed, Hempel thought that explanation leads to understanding. So we understand given that we have an explanation. But if we look at what an explanation actually is, like a success, like we now know something that we didn't know before, it looks like the relationship is the other way. Like given that we had a certain degree of understanding of something, an explanation, and new information, now it makes sense. Like an explanation explains because it fits to a purpose of knowledge that we previously had.
Yes.
In this sense, in recent years in explanation artificial intelligence, there is a shift from these POSOC and TEOR techniques that look for a very specific explanation of an algorithm to something that is called the stakeholder desiderata, which is trying to give an explanation adequate to a particular stakeholder's goals, objectives, previous knowledge, and so on. So this is, I guess, that is an example that and fortalece your argument. Strengthens. Thank you. Your argument about how shifting from explanation to understanding can have some practical, like success. It could be useful in the sense. So my question is, what do you think about this relationship between understanding and explanation, and also in the context of the stakeholder desiderata, usually there is a replacement of explanation for justification. So a good explanation is like a good justification in a given logical system to infer with certain degree of probability, certainty, and so on, a prediction to be the case. So this is my other question. What do you think about this trick? Like,
okay, so regarding the first part, you're right that for Hempel and for many people, like Karim Khalifa or something like that, someone like that, all you need is an explanation, and then understanding is just a byproduct of the explanation. I'm not trying to switch things around and say that understanding gives you an account of what an explanation is, because I'm not trying to define explanation. I'm not trying to give criteria for what makes something an explanation. What I'm saying is you will be able to say that certain explanatory methods in XAI are better than others simply because they provide more understanding than others. That's all I'm able to claim. And I don't really care for any specific theory of explanation applicable to those methods. So that's the first part. regarding the second part, I think there's an important tendency within the XAI community, or at least from philosophers within that community, to say we don't just want explanations. We want more than explanations. So there's a paper by Emily Sullivan and Natusa Kassir-Zadeh, which is going to come out very soon as a chapter in a book, in which they argue that we don't just need actionable explanations that make systems actionable in terms of you can change factors, but you need to make sure that the factors that a user is going to be able to change are in some way important to those users. There should be a pragmatic element in the way that we frame the explanations and make the models actionable, so that they somehow have an ethical component in terms of how useful they are for the specific users. And also last week I heard a talk by David Danks, and he was arguing that again, that we don't need only explanations in terms of which pixel was the one responsible for the prediction, but that we need to go beyond that and look for justification and look for ways of that the methods will give us justification for using that model. What elements within the model are responsible for the outcome is just a necessary but not sufficient condition to adopt an XAI model. We need to make sure that the model itself offers physically worldly grounded, let's say, a causally grounded account of how the model is representing the reality. So that's like the tendency right now in XAI is towards those two things. Mm-hmm.
So I have Dana, I have Jake. So Sig, do you want to be added to the list? No? Okay, Dana.
Ok, yo creo que necesito como hacer un recuento. Lo voy a hacer en español, perdón. Voy a hacer como un recuento para ver si entendí bien lo que está usted proponiendo. Lo que nos interesa no es transparentar la caja negra de las redes neuronales profundas, sino más bien utilizar los métodos de
XAI
no para entender lo que está pasando adentro, sino para que nosotros, como seres humanos, sepamos usar lo que nos está diciendo la inteligencia artificial explicable sobre el modelo de red neuronal profunda. ¿Es esa la idea?
Okay, I'm going to translate the question. The question is whether I'm proposing that that we're not interested anymore in making the black box transparent, but instead we're just trying to make sure that the model is useful for users, right? Okay. Not exactly. I mean, the idea of XAI methods, of using XAI methods, is still there. We're still trying to make the model more transparent in some way. But what I'm suggesting is that to assess those methods, to see if we can continue using them, we have to look at the outcome in terms of understanding. And that, well, the question is, how do we analyze that type of understanding that's being produced by the methods? That's more the project.
Yeah, thanks for the talk. So first thing, I just wanted to press Otavio's point about DN explanation just a little bit more. Just to say that, like, I don't know if Hempel specifically said this, but a common response at the time when people were advancing counterexamples to the DN theory of explanation, like the flagpole example, where the length of the shadow lawfully entails the height of the flagpole. I mean, they just, a lot of DN advocates just bit the bullet and they said, yeah, that's an explanation. It lawfully necessitates that, by deductive logic, the height of the flagpole. You may have, we all may have a problem with that, but that's just strictly speaking a problem with the pragmatics of explanation, not a problem with actual law-like explanation, right? And so obviously many of us think that's crazy, but it's not strictly speaking, it's not strictly speaking just like a false claim or something like that. It's self-consistent with the DN theorist's idea of what they're doing, right? And so I think like that's just echoing agreement with Ottavio that you're right on the actual case, because to many of us that's just a counterexample, or that kind of move is just a total failure to address the problem. But it's self-consistent, at least by the DN theorist slice, that it's not at all explainable in human terms, right? So that's just the first thing. And I guess the second thing, which is sort of related, is I was thinking about what sorts of explanations you are possibly going to get in AI systems, right? And so I was thinking along Dave's lines a little bit in various sorts of ways. It seems like what you're going to get, it's clear that what you're not going to get is like DN, or maybe you'll get some really broad inductive statistical things, right? But really what you're going to get more is kind of piecemeal understandings of contributors to the output, by looking at individual mechanisms and breaking them down the way Dave was talking about. So like you're going to get some mechanistic explanation of like edge detection, and then some mechanistic explanation of the classification scheme, right? Because you can look at training data and stuff like that. That's not going to fully explain all the possible cases, right? But it is going to at least explain, among other things, it's not exactly a surprise that a cat gets classified as a cat image gets classified as a cat when the model is good, or something like that, right? And so then maybe what we should be looking for is actually more into things like singular causal explanations and kind of these more piecemeal explanations, and as providing like a degree of understanding, right? Rather than this kind of all or nothing global sense of input output, like relations, which we're not really ever, I think I agree with you that we're not really ever going to be able to kind of, get a grasp on, because they're primarily statistical operations across like hundreds of layers or thousands of layers or whatever. So it's just not going to be relevant to us. But that doesn't mean we can't get any explanation, of a model whatsoever, right? You can still have partial explanations of it. Does that make sense?
Yeah, I think it depends a lot on the kind of example that you're thinking of.
Yeah.
If you're thinking of the cat, you can just say, oh, look, it was looking at the whiskers, or it was looking at the nose, or something like that, and then you get some sort of understanding of what happened in that particular case. But if you have a more complex situation in which you have like the bank loan, and you have all sorts of factors, or if you're using some kind of algorithm to decide whether somebody should go out on parole or something like that, the idea that you can just pinpoint exactly which one is responsible makes less sense. So I wouldn't. That's why I'm not very keen on the idea that there's a common element to all explanations in AI that help us, because I think it depends a lot on the specific use of the system. And if I say that it depends on the specific use of the system, then I'm just taking a pragmatic step towards what kind of users you're talking about and what kind of function it is performing within those, medical AI or the penal system or something. So what I want to see is the kind of users that are specific to those areas, and see whether the system is doing what is helping users and developers in those specific areas. That's the thing. About Hempel, I'm not sure I understood your point. What happens if one bites the bullet? I mean, it doesn't really make any difference in this case, I think, because you don't even have laws to begin with. So
well, it might affect, among other things, if we're already dropping the factivity, requirement, and instead substituting something like an explainability requirement or something like that, it might threaten the explainability requirement, because a DN model person might just say, that's just more pragmatics. I've explained everything I needed to explain, right? You may not like it, but that's pragmatics, right? Or something. That's like about how we accept explanations in speech. Yeah, but I agree that that's not a satisfying response, but it's at the very least self-consistent on the part of the DN theorist too.
Right. I mean, but that goes back to the beginning of the talk. I think that's a trivializing explanation.
I can agree.
Okay. Yeah. Okay.
If not, I have a question. I really enjoyed the progress. You all noticed, but and I'm very sympathetic to your standpoint. So I was wondering about how much work do we have to do as human agents once we are not that focused on asking the explainable artificial intelligence to provide us with explanations that we see as explanations, traditionally speaking, and so on. And what I had in mind is, in the case of philosophy of science, when we are talking about scientific understanding, I'm again very sympathetic to the idea that an output works very well if you can embed it into a theoretical structure. It inferentially it reinforces something, and you have success. But in those cases in which you don't have that theoretical structure, how much can we actually assess mistakes and the illusion of having understood something through an output which quality is very much mistaken or very deceiving, in the sense that it's very simple, but because of other computational issues like accuracy paradox, we have already know that that simplicity might be a red flag. So how can we assess understanding in those cases?
There's an article in the GDPR, the main framework for AI ethics in Europe, that says that the explanation that a company offers to the user has to be so simple that a child should be able to understand it. That's a very, very difficult possibility. Yeah, what age is the child? Yeah, so I mean, obviously that's going to be an impossible task to fulfill. But in many cases, for example, there's a random forest, which is a combination of many decision trees, which is opaque. That's used to assess whether a patient is high risk or low risk for diabetes. That's a very successful machine learning system, and it can when you use a global XAI method to turn it into a very simple decision tree. I think that decision tree in particular can be explained to almost anyone, any person who goes to a medical office, to a doctor's office, and that's the kind of thing we want, for the explanation to be understandable by the targeted user, and that's highly contextual. I'm not sure if I am responding to your question. And the cases I'm interested in right now, this is part of a new research project. I'm trying to understand the use of AI in scientific research. And in those cases, well, the explanation might be just very, very sophisticated, and doesn't have to be popular or understandable by a child.
Anybody else? If not, let's take Andrés, please. So for the speakers, lunch is served where it was yesterday. If you want to give your backpacks in the office, I think you can leave the room.